On your way out, don't forget to pick up your stuff in your folder and turn in what's due. This is what's due. So we are on day 4. Okay. Mel, what do we call this equation? It's just an S. Some German guy. Schrödinger equation, right? And H was what, Jeffrey? She have a little hat there. The Hamiltonian operator. And what's this guy, Kevin?
Wave function.
The wave function. The way it's written, is that wave function, Alyssa, an eigenfunction? The way this equation is written, is that wave function an eigenfunction of the Hamiltonian operator? Is it an eigenfunction? Does it fit that format of what we said was eigenfunctions and their eigenvalues? So you get the operator has to operate on a function. You get the function back again, the exact same function, and some kind of number. Yeah. The eigenvalue, Gloriana, is what?
Is it eigenvalue? Is it e to?
It's E. It's just E, right? And what's E, Jeff?
Energy.
Energy. And there's some different expressions for energy. We already had some already, right, in the last class period. Okay. So far, Melissa, we've been talking about V, and we've been saying every single time that V is what? Big V.
Zero. Oh, equals 0.
We said it's 0. And we've always been talking about a box, which really isn't a box, right? It's a line of length L, right? You said it was 0 in there. But now, talking about a harmonic oscillator. Kevin, is that the case?
No.
No. Here it is. That's how they want you to draw the potential energy V. Okay. That's geometric shape drawn in green there, Melissa. Is what geometric shape?
Outline green?
Yeah. Parabola. Okay. And there's a general equation for parabolas. You remember what the function was? Yeah, something squared, right?
Quadratic.
Yeah, quadratic. Y equals x squared. So here we're not going to say y equals x squared. Our y is our v. Well, here's our v. And that's equal to, well, you have the x squared in there, but what's the part in front of it? The springs and...
Negative K. The spring constant.
You have the spring constant in there. Missing one other little thing. When you had the potential energy of a stretched spring, x is the displacement, right? The distance that it's pulled from its equilibrium position. K is the spring constant. We're just missing a little half. V is 1/2 kx squared. So we're still talking about a particle on a line, pretty much, because it's just one dimension. But the only time it feels 0 potential energy is where? In the very center of this line, right, that it can go on, the very center of the line. So you take that line, right, kind of like this, in the very center, that's where the potential energy is 0. Take this whole thing and put it on its side. Here it is, a spring, right? Because that spring, as long as that weight is right there in the center, if I could stop it from bouncing, that's where V equals 0. So x is just how far I pulled it from 0. So they really want to see its displacement. So we used to think x goes between 0 and L. Well, not really anymore. Now we're saying that this is 0. So that's the displacement is 0. Then it goes out this far and can go out that far. But the farther it goes out, man, the potential energy gets, the bigger the displacement, whether it's positive displacement or negative displacement, the bigger the displacement, happens to potential energy. Skyrockets. Is that how it works? Right? Pull this down. Does it get harder and harder to pull it?
Yeah.
Yeah. In fact, if I let go, where does it have more potential energy? Here or way down there?
Down there.
Yeah, way down here, because the displacement's larger. And it's not linear at all. It's parabolic, right? So this is a much better model for a bond, right? Double bond, single bond, whatever, because the electron's in the center. Electron is what charge? Negative. The nuclei, Melissa, on each carbon atom, they're positive, right? So you'd think, oh man, you should just get pulled this way or pulled that way, right? And the farther it gets to it, the harder it's pulled. But they're trying to just get to the idea that we're trying to model this so that the farther we get from this nice, comfy equilibrium position, the more energy you got to put into it. So it's kind of like saying, okay, if we're gonna stretch this guy, right? Yeah, it might be easy at first, little stretches, but the more you want to stretch it like a spring, the harder it's going to be pretty quick too. So they're trying to just replace the bond with a spring. That's what all they're trying to do. They're trying to replace these bonds with springs. And how could, if that's the case, what would be the difference between that one and this one? What would be the difference in the spring?
Like in the potential energy, or?
Yeah, I mean, I guess what I'm trying to say is, if it actually was a spring, which one should be easier to stretch, the double bond or the triple bond? The double bond should be easier to stretch, and the single bond even easier. So what is it about a spring that you can say, oh, hey, that spring's easier to stretch than that one? How do you characterize a spring saying that? Oh, that's a really stiff spring.
So how close it is, how close the corners are?
Yeah, maybe. But mathematically, what's the symbol? K. If you're going to stretch a spring, I think it was negative kx or something like that. And all they said is that, hey, if you have a big K, oh, dang. And this is the same K as the one that's right there, the spring constant. So if K is a big number, man, that is a stiff spring. Because it takes, even if you have a little displacement, it takes a huge force. So I guess that's what I'm driving at, is we can model all these different bonds just by changing the Ks, just by changing the spring constants. Okay. And it's kind of nice because you would expect at some point, it's going to get so hard to pull and stretch that you're going to break it. So it's kind of modeling. It's not a bad way to model what's going on in a bond. It's a lot better than this little electron in a box that's rolling around. Okay, but even that gave us some answers, approximate answers. Okay. Anything else I wanted to mention? Oh, well, let's try some of this stuff here. How about So this is supposed to be harmonic motion. How would you describe harmonic motion in words? Gloriana, what would you say?
It only goes in one direction. Not all over the place.
Oh yeah, okay, good. Yeah, that's true. It's in one plane.
Yes.
One plane. That's good. That's a good one. Mel, how about another observation?
The same rate going up as it is going down.
Ooh,
It's not getting faster.
yeah, that's a good observation. Same speed going up as it is going down. Jeffrey, another observation?
It's perpetual.
Yeah, it's going to keep going as long as there isn't any friction or wind and stuff. This will go on for a long time. Kevin, can you think of anything else?
Oscillates.
Yeah, it's very repetitive. Let me give you a hint. Where is it moving the fastest?
At the bottom.
The bottom?
Well, Mel already didn't. Because Mel said it's not getting any faster.
Well, she meant that kind of the rate of change. Well, from what I said that Mel said is that it's kind of the same rate of change going down as it is going up. I mean, it's definitely increasing and decreasing its speed the entire time, right? Because it's 0 on top, 0 on bottom.
Would it be in the middle?
In the middle's where it's going the fastest. And if you need an idea for a science fair project with a little grandson or whatever, this is a good one. It works really well. You get 9 tennis balls and a swing. And the little kid has to throw the tennis balls from each position in the swing, right? So let's say this is their swing positions, right? And they're going to throw the ball that way. So you have positions A, B, and C, right? And a little swing going up, and he's going to take the 3 balls, and when he's at position A, throw them. 3 balls in position B, throw them, and 3 balls in position C, throw them. Which position? And you know, the kid's a kid, so you can't throw them all perfectly at the same force all the time, but it surprisingly works well. Which position is going to allow that kid to throw the ball the farthest?
B.
And why B?
Because kinetic energy is greatest at B.
Yeah, he's throwing that ball really hard at B. Most kids guess C, because look how high he is, right? And he's farther over to where he wants to throw it. So a lot of kids guess C, but no, the answer is B, because you are moving really fast down there. It's a swing, man. And you know, kids don't swing just really slow. They're really swinging high. He wants to get really high in C so he can make sure his hypothesis is correct, right? And he'll even throw it a little bit harder at C because that's how kids are. They want to get the right answer. But you can't. But B knocks him out of the water. So it's pretty interesting. Anyway, another science fair project that didn't win, and what won? Volcano. Like every year. Isn't that? Yeah. That beat the radio wave blocker. That beat this. I've never understood it.
This is your son's science fair project?
Yep.
Just like the volcano, Dr. Smith.
Yeah. No way. Okay.
He's actually cannibal.
Oh, there's another observation we had. I'm glad I wrote this stuff down. Okay. What is something that is not changing? Okay, I don't know, you'll observe it there, but this is going to be really hard for you to figure out, I think. Pull it down just a little bit. Whatever this is, it's not changing. I'm going to pull it down a lot.
Period.
Period. What's period?
The time it takes to complete an oscillation.
The time it takes to complete an oscillation is exactly the same. How would you count this? 1/1000. I don't know, you'd have to almost get a clock here, right, and time it. And to time it to go from hit the top, go to down and up, it's going to be the same all the time. 1/1000, 2/1000, 3/1000, pull it down even farther. 1, 1,000, 2, 1,000, 3, 1,000. Little bit. 1, 1,000, 2, 1,000, 3, 1,000. See, it's the same. So, but usually we don't talk about periods. We talk about, starts with an F, frequency. So you can say the period doesn't change, but people are going to say, what? It's a frequency. That's what they usually say. The frequency doesn't change. And what's kind of nice, and it's important, go back to this idea. We want to model a bond with a spring. Well, if you remember, what type of spectroscopy, instrumental people, are we talking about if we're talking about stretching springs with bonds? What instrument upstairs? FTIR. You got all these tables of all these stretches, they call it, right? They have their own terminology for all this stuff. And this carbonyl stretch, it stretches at 2720 wave numbers. Well, oh, that's only if it's in the ground state? No. It doesn't matter what the amplitude is of that vibration. It's the same frequency. It can jump from one, right? So but does it absorb? Yeah, it absorbs, right? So how can it? I mean, let me get it this way. If a carbonyl absorbs energy, what changes in the frequency? Right? The carbon action's bouncing around, they're stretching. The frequency can't change. What does change? Give it some more energy. Frequency doesn't change. B starts with an A. The amplitude changes. That's all that changes, right? And then, now if this was a carbonyl, right? There's a carbon in the oxygen here. If it was, can I pull it down and displace it any distance I want? Thinking quantum mechanically and what goes on in this weird microscopic world. Do you think I'm going to be able to pull, like this spring, I can pull it down any distance I want and get it to vibrate? Think that's going to work with the carbonyl?
Why not?
No. There's only certain distances, certain displacements. Because there's only certain energies, right? You have a vibrating spring. What two types of general energy can you say are going on here? What and what in general physics?
Gravity?
Yeah, you have gravity. Oh, gravity is, yeah. I'm thinking more general. So there's the P, potential energy and kinetic energy. You add them up and you get the total, right? So there's definitely more total energy with this vibration than there is with that vibration, right? There's different total energy. Frequency is the same. It's just the amplitude that changed, right? So that's where the energy is going into when these guys absorb. They're saying, hey, the amplitude of vibration changes, not the frequency. It can't. Okay, that's characteristic of the bond itself, the atoms on the end. Harmonic oscillator, possible energies. Okay. So how they get these? Well, they kind of jump to the answer. There's our E, right? They jump to this already. And after this, they'll tell us what the wave functions are they use. So anyway, that's how they did it. So you apply the Schrodinger's equation, right, to the Hamiltonian operator, and here's your energies. EV equals V plus 1/2 h bar omega. Remember before we had this particle in a box, and it could go between 0 and L, and the potential energy was 0 inside the box, well, the line essentially. But it had a 0-point energy. Does this have a 0-point energy?
No.
Yeah, you can't have 0 joules, ever. It always has to have some energy. You can't have 0. Okay. What's omega again, Alyssa? What's omega? Remember, this guy's omega. What was that again? Oh yeah, we had the symbol for. I think we used omega as a symbol for the eigenvalue, but here it's not supposed to be that. It's from the concept preview. You remember? Sorry.
was like, oh
I was trying to
my
get it
God.
softer. Omega is angular frequency, angular frequency, right? And remember, we had stuff like omega equals 2 pi f, that kind of stuff, right? So if we like to talk about frequency as hertz, Hz per second. Was that referring to f or was that referring to omega? When they talk about hertz,
F.
that's f, right? So if you want to talk about angular frequency, okay, it's omega. So that's the omega they're talking about. So if you don't like omega, just put in 2 pi f for it. Same thing. Okay. But with omega in there, the equations are kind of nicer. Like omega is the square root of k over m. What's m? Mass of, yeah, the electron in this, essentially in this, right, in the bond here, in the box. In this case, it'd be the mass of the weight, right? If let's see if this makes sense. Which m? Okay, here's that frequency, right? 1, 1,000, 2, 1,000, 3, 1,000. If I change it with a lower mass, what's going to happen to the frequency according to that equation? If I put a lower mass on there, the frequency should increase. So let's see if that works. 1, 1,002, 1,003, 1,000. Yeah, right? It definitely increased. Okay. So it works. And then they gave us these differences in energy levels. Do you remember the particle in a box? Melissa, do you remember those energy separations? Was it a constant number between these energy separations for a particle in a box? Yeah, it was changing, right? Wasn't it getting smaller and smaller and smaller? Yeah, well, that changed, yes. But if you fix the width of the box, those energy levels, they got closer and closer and closer the bigger n was. It depended on n. With a harmonic oscillator, it's a constant. It's a ladder. You have constant distance between steps in a ladder. So a harmonic oscillator is now if you wanted to say energies of a harmonic oscillator, using the word ladder is a really good description. Because look at that, those energy separations are constant. You just calculate it, so many joules, it never changes. It doesn't matter what V is. Okay. We got all that. Oh, how about throwing some terms? They say the word ground state in a homework question, or I say the word ground state of a harmonic oscillator. That just means what with all this talk? They say ground state. How does that mess with things?
But there's x equals 0 for like v equals 1 half kx squared.
It means V equals
0.
0. They say ground state because that's how they're counting their states. Right? V equals 0, 1, 2, 3. Just like the particle in the box, we had n equals, what was the lowest n, Gloriana? It was 1. So the ground state for a particle in a box is n equals 1. So if they wanted you to write the ground state wave function, you'd write the wave function for n equals 1. You want to write the ground state for a particle, you want to write the ground state wave function for a harmonic oscillator, you write it for V equals 0. Well, how do you do that stuff? Here it is down here. Right? So now they're giving us the equations. So V equals 0. Right? Now these are, we're going to see what they're looking like. Well, we could write one. Let's just write it. Psi 0. All right. I think I wrote down the page numbers here. Oh, you guys didn't bring your book, did you? I'll look it up here. I think I figure, oh, that's table 12.1. And we have here's our normalization constant. So what we need to do is you need to look in your book and you'd write down HV is they call these Hermite polynomials. And, oh, it's down here. And it's nice because they are orthogonal. Now, we had the word orthogonal a while back. Jeff, you remember what it meant? It had something to do with something that we're hardly ever going to see. It makes calculations really much, much easier.
The integration equals 0.
Integration equals 0. If I take, right, that equals 0. Just what has to be down here? Now you have these v's, right? Hermite polynomials. What are their v's? Yeah. It's called v and v prime. V and v prime just have to be what? And then integral 0. They have to be?
0.
No. They got to be different. As long as they're different, they're orthogonal. There's just as much positive area as there is negative area. You add it up, the total area is 0. So that's the idea of orthogonal. It makes calculations really quick for these computer programs. Okay, so that's why they picked these Hermite polynomials, because they are orthogonal. That's a big, big reason for picking them. Okay, so just make when v is not equal to v0, v prime. Sorry, when v is not equal to v prime, then it equals 0. So if they're the same number, what are you going to get? Assuming it's normalized, 1. Okay. Oh, here they plotted energy versus x. Okay. What do you think they're trying to say with these dark areas and white areas? What do you think they're trying to say?
Probability.
Probability of what?
Where the electron might be.
Where it might be, exactly. Probably where it might be. So if you see a white spot, you're supposed to say, oh, it'll never be there. But the technical word is, that's a, starts with an N.
Node.
That's a node. Right. So you could draw the wave function if you want. I know it's got to look something like this, right? The wave function looks like this. Right? That'd be the wave function. The probability density, remember, you just come up, 0, come up, right? Okay. And then they said, okay, for our wave functions for a harmonic oscillator, we always have this component, e to the negative y squared over 2. Well, they're just saying that's a Gaussian function, because it's the form e to the negative x squared. Okay. Oh, yeah. When v equals ax to the b, yeah, this is what the book says. B. Okay, so what they're trying to say is when the potential energy, when the potential energy is of this form, your variable raised to some power, and you've got this coefficient out front. Okay, whenever it's of that form, then brackets are supposed to mean what? What do they mean when they write brackets in this stuff? Average. I'm trying to say average. That's their way of saying average. It means integration and all this kind of stuff overall face. So they didn't just write E, they wrote EK. Kinetic energy. So twice the average kinetic energy is equal to that little coefficient, whatever your X is in your potential energy, that power, times the average V is potential energy. So twice the average kinetic energy is little b times the average potential energy. Well, our function is, I don't know why I'm writing it sideways like that. Our function is V equals 1/2 kx squared, right? So we're going to have 2 average kinetic equals my B, or sorry, AXB. Equals AX, so 1/2, where am I? Where's my B? I'm just playing around with it, just to show you that average kinetic is average potential. And it's not really that big a deal. It's just another observation that's really hard to get at. If you see this vibrating spring, you're supposed to, it's really hard to see it, but the average potential energy is equal to average kinetic energy. And that's really hard to see without the virial theorem, I think. Okay. So let's check out some of these. Do 11B in class. What the heck? I didn't type out 11B. What was 11B? I can use my book. Oh, I better hand these out. Here's our throw out Planck constant and bring in black body radiation.
What?
Planck. I didn't like, not Planck.
I was like, we just did that one.
Yeah, I like Planck. Boltzmann is the one I don't like. Sorry, yeah, don't throw out Planck. I like Planck.
Okay.
Am I short one? Oh, there it is. Oh, I've got an extra one here. So throw out Boltzmann, bring in this lab, okay? Okay, 11B. I don't know how I didn't get this one typed up. Oh, we're in chapter 12. Wrong chapter. Chapter 12, number 11. You know what? I might as well just show you that table 12.1 right away. Right? Because I wrote down table 12.1, but I didn't scan it or anything. You know what I'm talking about? To write the harmonic oscillator wave functions.
What did you say was in the parentheses
Oh, see, that's table 12.1. And then this guy is that e to the negative y squared over 2. Yeah, I didn't really finish that.
This last one?
Yeah, that's always the Gaussian function. Where's table 12.1? Oh my gosh. There it is. So on page 325 is table 12.1. So when they want you to write the wave function for a harmonic oscillator, you get the Hermite polynomial from page 325. So you just look up and see what V it is, and then you plug it in. Okay. And I'm sure the homework is going to have us do one of those. 11B. Calculate the minimum excitation energy of the 33 kilohertz quartz crystal watch. Calculate the minimum excitation energy of a 33 kilohertz quartz crystal watch. It's hard to even start unless you realize a quartz crystal watch exhibits what type of motion? Harmonic oscillator. It's a vibration. So it's a harmonic oscillator. So if it's a harmonic oscillator, here it is. Where's my pen?
Right here.
Oh. There's your distance between steps, right? Because, well, h bar omega is the first excitation. What do they want? Calculate the minimum excitation energy. So excitation energy means, okay, you're at V equals 0. Whoop. You're at V equals 0. I want you to jump up to V equals 1. That'd be the minimum excitation energy. They don't want you to go from 0 to 2 or 0 to 3. They want you to go from 0 to 1. So what is that going to be? Well, that's just h bar omega. So that's going to be h bar, and omega is 2 pi f. And we know f is,
33 kilohertz.
yeah, except make 33 kilohertz, but make the kilo 10 to the third. Yeah, so write 33 times 10 to the third hertz, and you'll get the right answer. That make sense? Okay, so 12.11b, calculate the minimum excitation energy of a 33 kilohertz crystal. Okay, so omega is 2 pi f, we're good. Okay? Part B is the bond between two oxygen atoms, in which K is 1177 newtons per meter. Again, minimum excitation energy. Well, I just say O2, right? So that's between two oxygen atoms. K is 1177 newtons per meter. Okay. So that's the second part of the problem. Well, it's the same idea, right? You want to go from V equals 0 all the way up to V equals 1. So it's h bar omega, except they didn't tell us what the hertz were. They told us what? K. So can you get omega if you know K? Yeah. Except we're just missing what? The mass. Okay. This is the trick. How do you get M? Do you find the molar mass of oxygen and divide it by Avogadro? Or is it more involved than that? Reduced mass. Someone's paying attention. Concept preview. We have motion. Right? Whenever you have these objects are moving around, that's the whole purpose of reduced mass. Right? Okay, what was the equation for reduced mass? 1 over mu equals 1 over, remember this? Yeah, m1 plus 1 over m. Or we use a's and b's, I don't remember, but that was the point. Okay, so in this expression, omega is the square root of k over m. What are we going to plug in for m again? What symbol? Mu. That's what we have to plug in. Okay, so how do we get little m1 and little m2? What are they again? What are we're talking about this. What's little m1 and little m2? Well, we don't know what the isotope is, but it's definitely what atoms? Oxygen atoms. So M1 is an oxygen atom. M2 is a oxygen atom. So that's what you got to calculate. How do you get an oxygen atom mass? What's that? Yeah, and molar mass of oxygen is like 15.99 or whatever, right? Divided by Avogadro. But don't forget to use what units? Convert it to kilograms. And you'll be good. So it's just like the concept preview.
Do you have the answers for these?
Yeah, I can give them to you. What did I get? for, I can't read my own writing. So this problem, I'll write them down right here. 11B, don't I have answers to 11B exercise? Don't I have answers to B exercises?
You just have 6.
I don't, shoot. All right, 11B had 2 parts. There's a part A and there's a part B. So the first part with the clock, I got 2.19 times 10 to the negative 29 joules. And then in part B with the oxygen molecule, I got 3.14 times 10 to the negative 20 joules. Okay.
I just said I have to go.
Okay. And then there's a part C. I'm adding this part C. Mel, I'm adding this part C, so you know. What wavelength of light? Is B. What wavelength of light is B? Okay. That's it. That's the only thing I'm adding. So what expression do you write to figure out wavelength of a light to make that excitation happen? Bless you. The energy of a photon equation. E equals h c over lambda. Or frequency, yeah. E equals h frequency, which is E equals h c over lambda. And then just solve for your wavelength. Okay. So you're comfortable with 11B? Alyssa, you see what to do? Okay. How about 7A? Let's make these bigger. Calculate the 0-point energy of a harmonic oscillator. Well, right off the bat, what does this part mean, 0-point energy? That means V has to equal its lowest number, whatever's possible. And in this case, it's 0. Right? So 0-point energy doesn't mean, you know, that's what the quantum number is, but it just means the lowest. Right? They give you the particle mass, they give you the force constant. Well, that's even easier than what we just did, right? Before, here there's no reduced mass to calculate.
So it's just V equals 1/2 kx squared? Or
They want the 0-point energy. So what they want, they want this. They're not, notice the difference between 0-point energy and this h bar omega thing. H bar omega is this. This is h bar omega every single time, right? And when they want 0-point energy, they're asking for this guy right here. What is this energy right there? What's that energy going to be? Well, it's not h bar omega. Well, it might turn out to be that, but this is the equation. This is how you get the energy at any state. Just plug in the V, and you can get the energy at that step, right? V equals 0, 1, 2, 3, 4. So they want the 0-point energy. They could have just as well said, well, we want the 4th excited state level. Well, but no, they want the 0-point energy. So you plug in V equals 0 into this expression, and you'll get it. Right? You just have to know what h bar is. H bar is Planck's constant over 2 pi. In omega, you're going to use what expression, Gloriana? Because they gave us, oh, I forget. 2 pi f. If they gave us frequency, that would work. Oh, they gave us the mass and the force constant. So you have to use what to get omega? Yep. Let's watch your units. I think they gave us everything in the right units. Okay. So do you see how to do 12.8? Alyssa, how would you handle 12.8? The difference in adjacent energy levels is this many joules.
You would use the harmonic oscillator equation, the E plus minus V equals H hat omega.
That's the question. Is it going to be that one, or is it going to be, because there's two energy equations for this harmonic oscillator, right? It's this one that you mentioned. It's this one. Then you've got this one.
That's what I said.
Which one? A or B? Let's label them. What's that? B. Exactly. Because they said adjacent energy levels. So you have to use this one. H bar omega. So set that equal to H bar omega. And solve for what symbol, Jeff? Solve for? K. Not bad, right? How about number 9? Calculate the wavelength of a photon needed to excite a transition between neighboring energy levels of a harmonic oscillator of mass equal to that of a proton and force constant. Anybody want to take a stab at this one?
You gotta use that A equation.
Gotta use this one? What's the guide that kind of tells you which one to use?
Or no, excited transition.
Yeah, they're talking about a transition. They're talking about going from one state to another state. It's going to be B again. You're going to have to use that H bar omega equation. Set that equal to what? Okay. Energy of a photon. And that energy of a photon is really equal to what?
H frequency.
H nu, okay, which is equal to HC over lambda. There it all is. You got it all. Right? And then for the omega, substitute in what? Square root of K over M. Oh, but hey, Alyssa, you see this? You see a problem? When you substitute omega as the square root of K over M, what do you use for little m? Because they told us the K is right over there, 855. What would you use for a little m?
Little n?
Yeah, because you're going to have h over 2 pi square root of K over m. Isn't that what omega is?
1.0073. But don't you have to convert it to kilograms?
There you go. Convert that little u into kilograms using that concept preview that we talked about. So you can't plug in the u units. It needs to be in kilograms. So convert it into kilograms, and you'll be good to go. Padawan's getting nervous here. Are we going over our limit again?